Hello, welcome. Hello and welcome. Good day and welcome to this Learning Space webinar. Testing 1, 2. Okay. I need to push your volume up. Testing 1, 2. It's number 2, this one. Testing 1, 2.
and welcome to everyone. Thanks for joining us on this wonderful Learning Space Tuition webinar, where we'll be covering Euclidean geometry, focusing on circle theorems. We really want to thank you guys for forming part of this, and I want to tell you guys we still have a few minutes before the webinar actually starts. Please send your guys, friends, the link to join us. Let's try and get this movement going. We want to get as many people on this webinar as possible, so we can all make maths super easy and all pass maths and do really well. Today we're going to do some really awesome stuff. You're going to meet a phenomenal educator, the Heinrich Cox, who's going to be our main presenter for the day. Introduce the concepts of circle geometry, make them super easy for you guys. He's got a secret guest. I'm not going to, but trust me, guest. Maths is going to be like so easy for you. You'll never feel ever again. And what I'd like to always again encourage you guys is to really make you guys in chat. Please note, as the video has been saying, engage in the Q&A section, not the chat section. So you've got a question, go into the question. Here's a question that you wanted to ask is already there. We've got a free upvote. Simply go to that question, click the thumbs up, and it'll sort of tell us and our moderators that this is a question that really needs to be answered. And if we can answer the question in the chat, we will. Otherwise, we'll leave it for our brilliant mathematician, Mr. Heinrich Cox, to address at the end of the session. Again, because this is a very interactive session, we're going to have multiple formats of how you can engage with us. First of all, we're going to introduce a poll. So a poll is simply where questions come up on your screen. You get to give us an answer, yes, no, multiple choice. And we basically want to see how well you guys are able to engage with us in this webinar. And we're going to have several polls. We're going to start with one very shortly. And then I want you guys to just sort of answer as best as you possibly can in that poll. So I'm going to ask our technical team to get the poll up, and then we will see what answers you guys pop up for us. Okay. Introductory poll up, which again, it's asking what grade are you in, which province are you from. So if you guys could please answer those two questions, and then the last question is, how do you find this topic in terms of how hard is it for you, how easy is it for you? So please go ahead. Thank you so much. I see all the answers are coming through already. This is fantastic. Okay, pretty easy, pretty simple. So we're going to keep throwing these polls at you throughout the webinar, and that's how you're going to engage with us in this webinar in terms of giving us answers back. Fantastic, guys. At the end, we do have some super awesome giveaways. You might have seen it as the webinar was leading to its opening, where please follow us on our Instagram, follow us on YouTube, all our social media platforms, Facebook. And at the very end, we're going to be selecting one person from each social media platform, one person from Instagram, one person from Facebook, person from YouTube, who's going to have a one-on-one private lesson with Mr. Heinrich Cox, which again, if I was in high school, I'd be super jealous for that opportunity. So please go ahead, follow us on social media, follow us on those platforms, and keep going and checking regularly for new updates, for new videos, and new awesome ways. So at this point, I'd love to introduce our for the day, Mr. Heinrich Cox. Mr. Cox, how are you doing?
I'm doing very well, thank you. And thank you so much, Ernest, for that lovely introduction. I really hope that everybody is going to find this to be such a useful and hopefully a pivotal section for you going forward. So that rather than, I was looking at the poll here, that this is a section that many of you find really difficult. And we're hoping that today, after this poll, you're going to have some more tools to be able to approach this section and maybe even start to enjoy it. So I'm really excited to get going. And I think we should do just that. Right. So, as discussed today, we are talking about Euclidean geometry, right? So as you expected, right? And to introduce this topic, I want to tell you that Euclidean geometry is a lot like learning to drive a car, right? So when you learn to drive a car, you've got to learn a few things, right? So the first thing is you've got to learn the names of the controls. So you've got to know this is a steering wheel, these are the brakes, this is the accelerator, here's the clutch, and here's the gear lever and all those sort of things, right? So you first have to know those basics. After that, you have to learn how these controls work together, right? So for example, if you want to change the gear, you first have to depress the clutch. If you want to turn, you first have to slow down and then turn the steering wheel. And then after that, perhaps accelerate out of the corner, right? So these things work together in particular ways. And then once you know how these things work together, you've got to go out and you've got to go practice your maneuvers, right? So you'll do taking off, coming to a stop without stalling, maybe parking, all these sorts of things. And then after that, you're ready to go out and drive on the real road without being a danger to yourself and others, right? So how does this apply to Euclidean geometry? Well, the first step is to know the names of the things in front of you, right? So I'm going to call these things the elements. And what I'm talking about is things like tangents, radii, center, words like segment, chord. What do these things mean, right? So we need to be able to know what this terminology means and what it refers to. Then we have to figure out how these things work together, right? So a theorem tends to combine some elements in some sort of logical way. So the tan-chord theorem, for example, will include a tangent, a chord, and an angle in the opposite segment, for example, right? So you first then learn how these things work together with the theorems, and then you're not going to go straight out onto the road, right? So you're first going to practice some of these individual theorems. So this is where, if you have a textbook, it's a good idea to go through the exercises before you get to the revision exercise at the end, or whatever you have that's been provided to you by your educator, or if you are privileged enough to perhaps have some extra help from a tuition, you can then some exercises that's going to help you build up to the final thing rather than throwing you in the deep end at the very end, right? And then the last thing is to go out and drive, right? So that's when you do your past papers, the complex riders, the things where you look at it and you're like, whoa, what's going on here? There's a lot of stuff to unpack, right? So let us then start with this in mind, right? So the first thing is, it's going to feel a bit basic, but we're going to pick up pace, right? So the first thing is the circle anatomy, right? So when we think about the circumference or the circle itself, it's blue, right? Center of the circle, radius, line from the center to the circumference. Diameter is a line that goes from one side to the other side that passes through the center. And then a chord goes from one side to the circle to the other side of the circle. Doesn't necessarily center, right? And then a secant is a line that's going to intersect the circle twice, but it just continues as much as it wants to, right? So those are basics. Let's make it a bit harder, right? So concyclic is a term that means together on the circle, right? So concyclic, if points are concyclic, then all of those points fall on the same circle. Now, a cyclic quadrilateral is basically a quadrilateral where the four vertices, those four places where sides join, are concyclic, right? And then opposite interior angles is what you see there in the yellow, right? So opposite interior angles would look something like that. And then an opposite exterior angle is basically if you just extend one side of the quadrilateral, right, then you end up with an opposite exterior angle. So just be very careful. Sometimes you might have something like that, like an angle that looks like that, and then you've got something like that. Now, that's not an opposite exterior angle because it wasn't formed by extending one of these chords that actually form part of the cyclic quadrilateral. So just be careful of that misconception, right? So here's another example of an opposite exterior angle. And then there's this concept of a tangent, right? So the tangent is a line that's going to touch the place, right? So then into this. So when you have a chord, the chord is going to divide into, right? So the minor segment is the smaller of those two segments, for instance here indicated in pink, and the major segment is going to be the larger of those segments indicated here in green, right? Then the minor arc is basically if we go from the start to the end of the chord along the edge of the circle, and that's going to be the shortest route, whereas the major arc then is what you get if you go the long way around. Okay. So let's look here at this angle ACB, right? So angle ACB here, the terminology we use is to say that chord AB subtends ACB, right? So if you follow the two chords from C to the points A and B, right, then you'll see that that AB is what you get to, right? So that's a visual there to show you what it means when we say AB subtends this angle ACB. Now, not only can chords subtend angles, it is also true that arcs can subtend angles, right? So this arc here, AB, can also be said to subtend this angle ACB, right? And then it's possible for a chord or for an arc to subtend more than one angle. So here you can see that this angle ADB is also being subtended by the chord AB. And that's when we use this terminology, angles in the same segment. Because if you look at that segment that is created by AB, any angle that is in that segment, right, is also going to be subtended by AB. So if I put another angle there, for example, with my brilliant handwriting, then you can see that that angle there as well is being subtended by AB. It is also an angle that is in that same segment. All right, so this is where we get to meet the person who may help you going forward with your Euclidean geometry. And that person is going to be Dr. Cape Town. Okay, so Dr. Cape Town, as silly as it sounds, is a bit of a mnemonic device, if I can pronounce that correctly, that helps us to find a starting point by which we can actually approach these riders. So what happens with a lot of students is you get to the exam and you've got this diagram in front of you. And this diagram is very, very complicated, right? And it's not so easy to know where to start. Now, when we apply theorems, the way in which we do it is we identify which elements are there, right? And whether the necessary elements are there in order for you to make some further, not assumptions, but to know that something else must be there as a result. Okay, so this is just an explicit way to do what you already do implicitly. Right, so what does this stand for? So the D is going to stand for diameters, right? So this is your starting point. So you look at your diagram and you identify whether you have any diameters. If you do have a diameter, then you know that the diameter is going to subtend a 90-degree angle. Or for example, you will know that the diameter, as with a radius, is going to be perpendicular to a tangent. Next up is then to look for radii. So for radii, one of the most important things you can do is to always make sure that you mark the radii in the same circles as being equal in length, because this is often going to lead to isosceles triangles, which we know have equal angles opposite the equal sides. Right? For the radii, you also want to see whether there's a line from the center that's, for example, perpendicular to a chord, or that bisects the chord, or that sort of thing. Next up is then to look for a center, because we know that the angle at the center is going to be twice the side of the angle subtended by the circumference, by the same thing. Then look for cyclic quadrilaterals, right? So here, it doesn't necessarily have to be a cyclic quadrilateral. You can also just have 4 concyclic points, which then allows you to maybe use the angles in the same segment theorem. And then the little known, most ignored theorem that most people forget is that when you have chords that are equal, they subtend angles that are equal. Right, so our Dr. Cape Town has 3 C's, center, cyclic quadrilaterals, and chords that are equal. And then the P is going to be for parallel lines, right? So we know about alternate, corresponding, and co-interior parallel lines. And then finally, the T is for tangents. We've got to look for tangents and then apply the theorems that pertain to tangents, right? So if you've got your rider in front of you, what I recommend you do is you first read all the information, read the questions, and then apply Dr. Cape Town, right? Now, when you apply Dr. Cape Town, by the time you are done, hopefully you would have extracted all the information that you possibly could from that rider. But you've got to make sure that you've always got your toolbox with you. Right, so the toolbox are those things that we sometimes forget that we're not explicitly looking for, but that we can use each and every time that it pops up. So for the toolbox, we're looking for VIP tips. Okay, so what are these VIP tips, right? So what you've always got to have in your back pocket is the idea that vertically opposite angles are equal, right? So as soon as you find an angle and you see it's got a vertically opposite angle, you want to mark them as being equal. The I is for isosceles triangles, right? So for isosceles triangles, we know that the angles opposite the equal sides are going to be equal, or that if you've got equal angles, that you must also have equal sides that are opposite those. The P is going to be for a point. So this we don't use that much, but frequently you have 1 or 2 or 3 angles around the point, right? And then you can use the fact that they all to 360 degrees to possibly find anything, right? Then, very importantly, always the third angle triangle, right? So sometimes we find an angle and we don't realize that we've actually found the second angle in a triangle, which means that we're able to go find the third angle in the triangle by virtue of the fact that the 3 angles in a triangle always add up to 180 degrees. And then the other P is going to be for Pythagoras, right? So Pythagoras we don't always use in Euclidean geometry, but as soon as we have 90-degree triangles, we know that it is a tool that is in our toolbox that we've got to be ready to use, but it's often more useful when we're actually interested in the length of sides and not so much the size of angles. So use your judgment on that one. And then S is going to be for straight lines. We know that the angles on a straight line are going to be equal to 180 degrees, i.e. they are supplementary. Okay, so now you've got a method to approach. You've got that Dr. Cape Town, you can use all your theorems, and you've always got your toolbox in your back pocket that you're every time find an angle and you see any of these things are relevant, right? So then the next thing is to just communicate to you some really important principles that are going to make your life easier when it comes to Euclidean geometry. Okay, so the first principle is this. The diagram is your guide to writing correct answers, right? So you analyze this diagram, you apply Dr. Cape Town, you do your things, and then you go to the questions. Now, you are going to refer to your diagram for each of those questions that you're trying to answer. So your diagram needs to tell you the story as clearly as possible. So it's very important that your annotations are going to be neat and tidy. And this one I know is controversial, but I actually recommend that you make your annotations erasable, which means either using it in an erasable pen, there are such color-coded erasable pens, or to use a pencil, right? So I know that it's nice to use highlighters and all that sort of thing, but sometimes what happens when you use something like a highlighter to annotate your diagram is that you get what I call tunnel vision, right? You can only see that which you highlighted. And if it wasn't the correct thing, it's going to prevent you from possibly seeing something else that you didn't highlight, okay? And then the other thing is sometimes you work through the diagram and you just don't see it. You're not finding the thing. And then when you look at your diagram, you take a step back and you look at it and you're like, this is a mess. This is a complete and utter mess. And then at that time, your diagram is no longer useful to you. It's actually a handicap when it comes to answering the questions correctly. So at that point, when you've made a mess, you really want to be able to tidy up. And that's when it's going to be fantastic to be able to erase. So I do recommend that you use either erasable pens or that you use a pencil in order to annotate on your diagram. Then the next thing, and this is for me the golden rule when it comes to Euclidean geometry, you prove. Okay, so often we're asked to prove or to show that something is, for example, a pair of parallel lines, or to show that something is a cyclic quadrilateral, right? Once you have proven that parallel lines, all the theorems that pertain to parallel lines can now be used. So as soon as you show you have parallel lines, you want to now go back to your diagram and look, are there alternate angles? Are there co-interior angles, etc.? If you prove that something is a cyclic quadrilateral, in your diagram, there isn't going to be a circle, right? But you still have to be able to then go and apply the to that well, cyclic quadrilateral that you've proven that actually doesn't have a circle around it. Note, I don't recommend that you actually go and try to draw a circle around the 4 points when it's proven to be a cyclic quadrilateral, because that tends to make more of a mess. And it's also really difficult to get it through the 4 things, and don't do it. Okay. And then the last principle I want to communicate to you is to relabel when it is appropriate to do so. So what do I mean by this? So you might start with this particular problem that I have here and use angles in the same segment and go and call this angle Y and this angle Y. And then you say this angle is X and this angle is X. Great. But then you might find out that this chord is in fact equal to this chord. And then you've got that theorem of, okay, equal angles subtend equal chords. But now you've got an issue. That means that the angle X is actually equal to the angle Y as well. Side, fine. Everywhere that I've got Y, I've got to go change it and make it X. Okay, so you've got to relabel your angles when it's. I highly encourage you to use your diagram. So now, approach. You sit down, you read the questions, you apply Dr. Cape Town with your toolbox of in mind, and it's time to apply theorems. Or not the theorems, let's have a look at theorems. So Dr. Cape Town starts with diameters, right? We angle subtended by diameter at the circumference. So you can see here that this line here is our diameter, and it subtends that angle there, right? So that angle is going to be a right angle. And the reason we use is angles in a semicircle. So basically, when you've got a diameter, the segments that it divides your circle into is a semicircle. So any angle within that semicircle is going to be a right angle. And that's why we use that terminology. Right, so what's super important is that you keep in mind that the right angle is often a second angle in the triangle, right? So you might have already been given an angle, right, like alpha, or it was 30 degrees or something like that, right? And then you go apply this theorem and you go draw that little right angle thing. But sometimes in our minds, we don't go, oh, this thing here means 90 degrees. And then we don't see it as the fact that actually we've got the numerical value of a second angle in the triangle. So whenever you do go and find that 90-degree angle, remember your box of, or your toolbox of things. And one of those things is the sum of angles in a triangle. And then you've got to go and say, actually, that third angle is going to be 180 minus 90 minus alpha, which will then give you 90 minus alpha. Okay, so then the converse is also true, right? If you've got an angle and it's subtended by a chord at the circumference of the circle, and that angle is 90 degrees, then the chord is a diameter, right? And for that, you can just say chord subtends 90-degree angle. So next up, let's look at the radii. So super important, as I said, is to always mark radii in the same circle, or rarely in identical circles, super rare, as being equal, because they will be equal in length. And then what often happens is that those equal radii are going to form an isosceles triangle. So remember, isosceles triangles are one of those things you always keep in your back pocket. As soon as I show that I have an isosceles triangle, I want to go think about the angles the angles opposite the equal sides being equal, or the sides opposite the equal angles being equal. It's quite a tongue twister. Right, so we want to then show or conclude that those two angles opposite the equal sides are going to be, in fact, equal. Right, so then the theorem that we see most often with radii is that the line from the center of a circle perpendicular to a chord bisects the chord. So remember, we need to know our terminology. Bisects is just a fancy way of saying cut in half, right? So cut in half perfectly, such that the one side is the same length of the other side. Or if you bisect an angle, then the two angles that it creates are going to be equal.
Dissects are when you cut something into two pieces, but they're not necessarily equal. Right, so if you've got this, a line from the center that's perpendicular to the chord, then you can conclude that the chord is being bisected, right? So those two things are equal in length. And note that even though I've put this under radii, it doesn't have to necessarily be a radius. So often it is a radius, but it can also just be a line from the center, as I've indicated there. And that's then line from center perpendicular to chord, all right? Then if you have the line drawn from a center of a circle perpendicular to a chord that bisects the chord, right, then that is going to be perpendicular, right? So here you've got a line from the center. Now you've got the chord being bisected, and now you can conclude that it is in fact perpendicular to that line, right? And then the final one is basically if you've got a perpendicular bisector of a chord, then it's going to pass through the center of the circle. And again, it doesn't have to be a radius. Often it is, could also even be a diameter. And that's the perpendicular bisector of chord, right? So it might feel like I've run through this a little bit quickly, but I'll show you just now how we're going to bring all three of those theorems together in a lovely way. Okay, so here's a tip. Sometimes questions revolve around finding the lengths of line and not finding angles, right? And whenever perpendicular lines or right-angled triangles exist, as we said in your toolbox, you are looking to use the theorem of Pythagoras, right? Now here, especially when we've got this theorem, you've got to be ready to construct a radius to complete the right-angled triangle, especially when, as we said, you know the length of the radius. So what do I mean by that? Let's say, for example, they tell you that this radius is 10 units, right? And maybe they tell you that this line here is 5 units, right? If you want to go find the length of this line, for example, you can go draw in this radius, and because all radii are equal, this will also be 10 units. And then you can use Pythagoras in order to go find the length of that line. Okay, right. So this is how we bring it all together. Now, these three theorems are not really three separate things. Sure, they've got slightly different reasons and all that sort of thing, but I think of them as being three pieces of the same puzzle. And no, I'm not referring to these puzzle pieces down here. That is just the logo for Learning Space. But it's three pieces of the same puzzle, right? And basically, those pieces are a line from the center, something that's being perpendicular to the chord, so that particular line, and the bisection, the cutting in half of that chord. Right. So if you have a line from the center and it is perpendicular to the chord, as it is indicated in that diagram, you know that it bisects the chord, right? If you, for example, have a line from the center that bisects the chord, you know it's perpendicular to the chord, right? Or if you've got something that's perpendicular to a chord and it bisects the chord, then that's a line from the center, right? So basically, you've got three pieces of the puzzle. If two pieces are there, you can always conclude that the third must be true. Okay, right. So let's keep going here. And now we get to do our first exercise, right? So what I'm going to do is I'm going to give you 4 minutes to first look at this exercise and see whether you can apply Dr. Cape Town, right? So apply Dr. Cape Town as well as you can, right? And then we're going to launch a poll where you are then able to answer one of the questions. And one of those questions will be, find the length of DB, right? So we want to find the length of DB, use Dr. Cape Town, and at the end of that poll, we're just going to talk about where on earth all these green things came from and what they mean. Okay, so for the sake of time, we can now continue, right? So we've got the results there, and we see there's a tie between 1 unit and 2 units, right? So let's see what the reality is. Okay, so if we go back here to this slideshow, then I just want to take some steps back to before the time where I gave you the actual questions and just read through this with you, right? So first thing I want to point out here is when we read FC as a diameter, what's sometimes useful, depending on whether we've got lengths involved or not, is to go and mark AF and AC as being equal in length because they are then radii. And since A is the center of the circle and AB is a radius, we want to go and mark all 3 of those lines, AC, AF, AB, as being equal in length, right? Then we're told CD equals DE, so we definitely want to go mark those as being equal in length. And then we're told FC is 10 units. Now here, the diagram can get really messy if you go and do something like this and say, this is 10 units, which means this is 5 and this is 5. So I don't recommend that you do that. What I do recommend is that you simply make AC 5 and AF 5, and obviously now AB 5 because they're all equal in length. And then if you need the information that CF is 10 units, well, you know that 5 plus 5 is 10, right? So you don't necessarily need to note that down. Okay, and then we're told CD equals 3 units, and because we were told CD and DE is equal, we then also just note that DE must also be 3 units. Okay, so that information in green, that's all that we get before we've even looked at the questions and before we've even gone and applied Dr. Cape Town. Right, so let us do the things and apply Dr. Cape Town. Right, so I'm going to start with the diameter. So when we have a diameter, right, we know that the diameter is going to subtend a 90-degree angle. So we know that E here is going to be a 90-degree angle, so we're going to fill that in. All right, nothing else useful comes from the fact that this is a diameter, right? So then we use our radius, right? Now here, AD or AB is a radius, right? And we see it's in fact a line from center that is bisecting a chord. And as we saw earlier, that means that it is in fact perpendicular to that chord. So that means ADC is also a 90-degree angle, and we fill that in. Okay, and then we have marked the radii as being equal, but unfortunately there are no isosceles triangles as a result of that. So we can leave that out for now, and then we can continue. So the first C is the center. Right, so we like to think about the angle at the center being twice the angle at the circumference, but that's not relevant here. Cyclic quadrilaterals. So we do have CBEF as being concyclic points, but it doesn't form a cyclic quadrilateral since CBEB doesn't quite exist as lines, and angles in the same segments also not useful because F and B are not joined. Okay, so that's not useful. And then the third C, chords that are equal, well, we kind of do have that, but they're not subtending angles at the circumference. Parallel lines we don't have, tangents we don't have, so now we can continue. Right, so first question there is we've got to prove that AB is parallel to FE. Now from Dr. Cape Town, right, we've already found that here we've got a 90-degree angle, and here we've got a 90-degree angle. And those are in fact corresponding angles, which then does show that AB is parallel to FE. But unfortunately, the examiner does not mark your diagram, the examiner marks your script. So we need to now actually go and take what we've surmised from our diagram and put it down into writing. So that's exactly what we're going to do. So we need to give a reason for why that is a 90-degree angle, right? So we can say that, I'm going to call it FEC, right? So my FEC, I'm going to say, is equal to 90 degrees. And yes, it is because of angles in the semicircle. Okay. And hopefully for the sake of your examiner, your handwriting is better than mine. Okay. Then we also need to say why that was 90 degrees, right? So for that, we can now go say, okay, we know that ADC is equal to 90 degrees. And the reason for that was we had a line from the center, right? And that line from the center bisected the chord. Okay, so our line from center bisected the chord, and as a result, we know that it's 90 degrees. And now we've got the corresponding angles that are equal, so we can there say, therefore, AB is parallel to FE, okay? And our reason for that is going to be that the corresponding angles are equal. We've got the equal corresponding angles. Now, if you think back to not so long ago, I told you I've got that like golden principle that like far stands out above all principles for me, and that is use what you prove. So we have now proven that AB and FE are parallel lines. So we're going to go put there that they're parallel lines, draw in our little parallel things. But then as a result, we might have some other things we can conclude. So if I go look there, I guess we do have co-interior angles with ADEF, but it's quite obvious that ADE is a 90-degree angle. But the most interesting for me is that we actually do have corresponding angles there. So CAD and CFE. And so we're going to go in our diagram, go put a note there for us. Here I'm just using some dots to show that those are actually equal angles. All right. So then we can continue. And the next question is telling us to find the length of DB. So this is what the poll asked. So we're going to find out now. Is it 1? Is it 2? Is it 0.5? Is it something that wasn't even on the poll? Let's find out. Okay, so in our toolbox, we've got Pythagoras, right? And this ADC is a right-angled triangle. So we're quite keen to use Pythagoras in order to find the missing side AD. All right, so we can go say that AC squared is in fact equal to CD squared plus AD squared, right? And then AC squared, we know that AC is 5 units. We know that CD is 3 units, and AD is what we're trying to find. So I'm just going to leave it as AD squared, right? And then you get 25 is equal to 9 plus AD squared. And then 25 minus 9 is 16, which is equal to AD squared. And here, when we square root both sides, do keep in mind, when you square root, you have to go positive, negative square root 16. But in this particular instance here, we're dealing with the length of lines, so we can ignore the negative. So when I square root both sides, I'm just going to write 4 is equal to AD. Okay, so that then is the length of AD. And so we now know that AB, right, so AB is this whole section here, has to be equal to the 2 line segments that make it up. So AD and DB. And DB is in fact what we were interested in, right? So AB is equal to AD plus DB, right? We know AB is 5 units. We just found out AD is 4 units, which means ding, 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 5 minus 4, 1 is equal to DB. So if you found 1 to be the length of DB, well done. That is in fact the length of DB. And then we have one more question to answer. And that, oh, actually, there was something important I wanted to note here that my animations are reminding me of. So let me just get rid of all my ink on the slide. So here, that 5, okay, is no longer all that much useful to us, right? Because now we know the length of AD and the length of DB. And this is again why I think it's a great idea to be able to erase, because I would recommend just getting rid of the 5 and then making the AD the 4 and the DB the 1. So you know AB is 5 because you know it's 4 plus 1, but it just makes your life a whole lot easier to not have so much messiness and to know exactly what the length is of each of those line segments. So then we continue, and we've got to find the length of FE. Now, the length of FE, there's actually a good few ways that we can find this. One would be the similarity of triangles, right? So that CAD and CFE are actually similar triangles. You can use the midpoint theorem, right? But I think the easiest is to note that CFE is also a right-angled triangle, right? And so as a result, the CF squared will be equal to CE squared plus FE squared, right? So CF we know is 10 units, it's the 5 plus 5. CE is 6 units, 6 squared plus FE squared, right? And then if you go and compute all of this, then you get 100 minus 36 is equal to the FE squared, which means that 64 is equal to FE squared, and the square root of 64 is 8. And so FE is 8 units, and we have answered all the questions. And at the end of the day, we've got that beautiful diagram with all that information on it. Right. So that was the first exercise. We can now continue and look through some of the other theorems that we would like to use in Euclidean geometry. Right. So the next thing for Dr. Cape Town is the 3 C's, right? So the first, the C, we said was going to be for the angle at the center, right? So when we've got that center there, the angle subtended by the arc at the center of the circle, right, is double the size of the angle subtended by the same arc at the circle, at the circumference of the circle. So what does that mean? So that angle 2x, you can see, is being subtended by that arc that has been highlighted there in pink, right? It is also true that this angle here, x, is being subtended by exactly the same arc. So as a result, this angle at the center becomes 2x, and that angle there is x. So our reason is angle at center equals 2 times the angle at the circumference. Now, this theorem here often causes a little bit of confusion because there's actually a few different shapes in which this theorem can appear. All right. Now, the first one we've already looked at, where we've got that arrowhead type thing going on. And then the next one is when you kind of get like a bow tie, but the fourth point of your bow tie isn't on the circumference of the circle, right? So here, if you have a look, that angle at the center is being subtended by this arc here. But this angle here at the circumference is also being subtended by this arc. So the theorem holds true, and we can label it as 2x and x. Then probably the one that people get most confused with is this one here, where it all looks like it's part of one big triangle, right? So here, again, this arc is subtending this angle at the center. So we can call that 2x, but it is also subtending this angle here, right? And so we end up with 2x being this angle at the center and x being the angle at the circumference there. And then finally, this one here, where we've got this quadrilateral, but not a cyclic quadrilateral, because that center there is, well, not on the circumference of the circle, right? Here, you actually have the 2x being subtended by what we would call a major arc, because it's the long arc and not so much the short arc, right? But then that angle there, x, you can see is also being subtended by that major arc there. And so we conclude exactly the same thing. This angle at the center, 2x, is going to be twice as large as the angle at the circumference, which we called x. Now, for this particular shape here, just note that the angles around the point is often going to be super useful to you, right? So this here, you'll often label as 360 minus 2x, or if you have a value for 2x, even better, you can just go 360 minus that value. And that's something that we actually often see in different types of questions. All right, so that's the center. All right, then next up, we want to look for cyclic quadrilaterals. So angles subtended by a chord of the circle on the same side of the chord are equal. Right, so there we've got an angle that's subtended by the chord that we've got in red. And then you've got another angle there in orange that's subtended by the chord, and that same chord is in red. So these two angles are going to be equal. And the chord doesn't actually have to be there. We can also just have an arc that is below those angles. And our reason is going to be angles in the same segment. Why? Well, if we keep that chord there and we look at the segment that is created, right? So the part of the circle that it divides the circle into, then those angles are in the same segment and thus they are equal, right? So that's what that angles in the same segment thing means. Now, just be very careful. This theorem is actually going to give you two sets of equal angles. And you've got to look for a bow tie, but remember it's a bow tie with all four of the corners on the circumference of the circle, right? So you also have angles in that segment there, and those green angles there are also being subtended by that red chord that I've drawn in there. And so those are also equal. right? Now, this theorem is closely linked to cyclic quadrilaterals, right? As there must be 4 concyclic points for it to be applied. So have a look, we've got to have the 4 concyclic points, right? But that's not actually a cyclic quadrilateral because those 4 points aren't joined like a quadrilateral, but you can see that it's closely linked to it because as soon as we join those points, we actually do have a cyclic quadrilateral. Now, be very careful not to get stuck with your particular bow tie, right? So as we look here, the bow tie that we have here, we've used is, if you allow me to draw these squiggly lines, we're looking at that bow tie there. But there's actually another bow tie that's in this exact same diagram. So if you follow this bow tie, it's almost like a bow tie in a bow tie, like bow tie inception. Anyway, then you will find that this here, this chord here, subtends this angle as well as this angle. So those 2 angles would have to be equal. And then same thing here, this angle here, this chord here is going to subtend this angle and this angle as well, right? So if you have a cyclic quadrilateral and the vertices are joined, the diagonals are joined like this, you actually get 1, 2, 3, 4, 5, 6, 7, 8 angles, and thus 4 pairs of equal angles, right? So don't get bow tie blindness. Don't look at just the one bow tie, right? If you've got the cyclic quadrilateral with the diagonals inside it, then you actually have 2 bow ties. Okay, so let us continue. There's a common pitfall that you need to be aware of, right? So sometimes we look at this angle here, alpha, and we look at this angle here, theta, and it looks so nice. Yes, this red line surely is a chord that subtends both of those angles, but no, those angles are not equal, right? And the reason is that in order for us to have angles in the same segment, all 4 of the points need to be on the circumference of the circle. And here you can see that green point there, A, or, well, it's not A, the angle is alpha, but that green point there is not on the circumference of the circle. And so we cannot use angles in the same segment. So be careful of that. You do have a bow tie, right? But your bow tie has to have all 4 of the points on the circumference of the circle. Now here the converse is also true, right? So if you've got your bow tie, right, and the bow tie has 2 angles that are subtended by the same chord that are equal, then those 4 points must be concyclic, right? i.e., right, those 4 points would fall on a circle. Okay, now note, even if you have the bow tie and that line isn't drawn, right? So you've got something like this, but you do have that this x and this x here are angles that are equal that were given, then you can also go and conclude that those are concyclic points, right? Now, super important is, again, one of the golden principles that I've got there in gold is use what you prove, right? So if you're in the situation here where you've gone and shown that this is now a cyclic quadrilateral, in your diagram, you don't have animations that's suddenly going to give you a nice circle through your 4 points that says, yes, well done, you found this. This is a cyclic quadrilateral. You're going to have still just exactly this. But then because you've proved that it is a cyclic quadrilateral, you can go conclude, yes, these 2 angles are angles in the same segment. And if this was joined, right, you'd also be able to go say that this angle and this angle are equal, or that this angle and this angle are equal, all because you've proven by concluding that because these angles are equal, you've got the 4 concyclic points and you have a cyclic quadrilateral. Because you've done that, you can use all of the results that go along with that. So you can use all the cyclic quadrilateral theorems. Use what you prove. Okay, let's continue. All right, so just through that. Okay, so now we've got these cyclic quadrilaterals where we haven't gone and joined the diagonals. And this is where we get our most common theorem, where the opposite angles of a cyclic quadrilateral are supplementary, right? And this is again where what I did at the start, well, I just showed you the anatomy of the circle and what these things look at, like why that is important. Because if you can't identify the opposite interior angles of the cyclic quadrilateral, then this theorem is useless to you. right? So the opposite interior angles are supplementary. They add up to 180 degrees, right? And that's an easy reason opposite angles of cyclic quadrilateral, right? And then the converse again is also true. If you can show that x plus y, these opposite interior angles are supplementary, then you can say that it is in fact a cyclic quadrilateral. And that's the opposite angles quad sup. Okay. Also, we know that the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle, right? And this, I almost feel affronted that it's a theorem on its own, because it's really just this opposite interior angles thing that's hiding in the angles on a straight line trench coat, right? So why do I say that? So let's say, for example, this is 30 degrees, right? Then because of the opposite interior angles being supplementary, this would have to be 150 degrees. And then because of angles on a straight line, this has to be 30 degrees, because angles on a straight line is equal to 180 degrees. So should it be a separate theorem on its own? I don't know, but anyway, it is what it is, right? So opposite angles of cyclic quad. Right. So then again, the same thing is true about the converse, is if you can show that the interior angle is equal to the opposite exterior angle, you can conclude that the 4 points are concyclic as a result. Okay. And then the third C for Dr. Cape Town, we said importantly, is that equal chords subtend equal angles at the circumference of the circle. And again, I stress that this is one that goes missing a lot, where I've got a student who's 85, 90%, they're trying to get full marks for this section. And when they get stuck on a rider and they just look at it and they're not sure what's going on, it's usually because they've forgotten this theorem, right? So this theorem here, if you've got the equal chords, they're going to subtend equal angles, right? So here in those two triangles, the purple one, well, it's not purple, is it? The pink one and the green one, you can see that they're subtended by those equal chords that I've now put there in orange. And that means that the angles that are subtended are going to be equal, right? And equal chords, equal angles. But there's more, right? It doesn't even have to be an angle at the circumference. If you have an angle at the center that are being subtended by equal chords, then those angles at the center are also going to be equal, right? And it's actually also true that if the circles are identical, then equal chords in each identical circle is going to subtend equal angles. But man, I have never seen that particular theorem in use. Anyway, okay, so now the fun part, we get to move on to exercise 2, right? So in the following, E is the center of the semicircle, ABCD is a cyclic quadrilateral, BAC is 30 degrees as indicated there, and ACD is equal to 25 degrees. So we're going to find the size of DBC, we're going to prove that triangle EBC is equilateral, and oh, there was only 2 questions. Okay, let's go back. So that's what we're going to do. And now I'm going to again give you 5 minutes in order to attempt this one here, apply Dr. Cape Town, and then our poll is going to ask, what is the size of DBC? Okay, so you've got 4 or 5 minutes, however long I feel like giving you, and then we will continue. Give that a go. Get back on screen. All right. Okay. So can we see the results of the poll? What do we got there? Okay. So we've got 25, 30, 35, 46%. So this time we've got a front runner. And then there's the 40 degrees there. Okay, so let's see what we're going to find here. Right. Okay. So the first thing I'm going to do, as per always, and I don't think any of you are going to be surprised, is I'm going to apply Dr. Cape Town. Right. So because we've got a semicircle, this AB here is a diameter, right? So any angle that is subtended by that diameter is going to be 90 degrees. So I see here that this ADC, right, is a angle that's subtended by that diameter, and also ACB, right? So I'm going to go ahead and I'm going to mark either of those angles or both of those angles as being 90-degree angles. Fantastic, right? Then we've got to go look for radii, right? So we know that AE is going to be a radius, EB is going to be a radius, and EC is going to be a radius. So we want to mark all of those as being equal in length, right? But then remember, you've got your toolkit, right? And the toolkit, the VIP tips, right, includes isosceles triangles. That's the second letter there, the I, right? So I'm looking here, AEC, that looks like an isosceles triangle to me. So I know that the angles opposite the equal sides are going to be equal, right? And so I know that this is going to be a 30-degree angle, right? And then, right, I also see that I've got here two angles in a triangle, right? Which means that I can always find the third angle. So then I know that this must be a 120-degree angle because it's 180 minus the 30 minus the 30, right? Then I see that I've got angles on a straight line, right? So then I already know that that angle there is going to be 60 degrees, right? So I'm not even using Dr. Cape Town currently. It's just my toolbox that's being applied here. You know, and then the next thing I notice is actually I've got this 90-degree angle here. I know that is 30 degrees. So then this angle here must be the 90 minus 30. So that's then 60 degrees, all right? And then because I've got the isosceles triangle, right, I know that this angle here must also be 60 degrees. Now, when I've got a numeric angle that's not something nice like a 90 degrees, that spans over two angles like it does for EBC. What I prefer to do is to draw a little line like that and then to write the 60 outside of it. And what that's going to do is when I need to go right an angle here, or I need to go right an angle here, it's not going to be in the way, and it's going to be easy to see what's going on. All right, so that's another pro tip for you. So then I've now applied the radius. Okay, I don't have radii that are perpendicular to chords or bisecting chords as far as I know, can't see that. So now C, so center, right? So what's nice here is you actually do have this angle at the center here, the 60-degree angle that is being subtended by that B there, right? But in fact, then we've already found it to be 60 degrees, but at least we now know that we're not surprised that we actually have that 30-degree angle there because we know the angle at the center is twice the size of the angle at the circumference that's being subtended by the same chord, right? And then the same thing here, this 120 degrees is being subtended by AC. So we're not surprised that this entire angle B is going to be equal to 60 degrees, right? So if you missed it with the isosceles triangles and the angles on the straight line, the way that I got those other angles, you had another chance at it because of the angles at the center. How nice is that? Okay, so then we are looking for a cyclic quadrilateral, which we definitely do have here. We've got A, D, C, B. Right. Now here, because we have the diagonals that are crossing like this, we definitely have a bow tie. And so we want to look to use angles in the same segment. All right. So let's see what we can get here. Right. So we can first conclude that this is a 25-degree angle because we were given this 25 degrees, and we can see that AD, this here, is going to subtend this angle as well as that angle there. So now we know that this EBD is 25 degrees. And then if we continue, right, we can also go and say that actually we know that the whole of B is 60 degrees. The one part is 25 degrees. So then the other part must be 60 minus 25. And so that's going to be a 35-degree angle, right? But now if we continue with our angles in the same segment, this angle here and this angle here are being tended by this DC. And so we also now know that that is a 35-degree angle, right? And then if we keep going, right, we know that this BC here is subtending this 30-degree angle as well as this angle here, D. So we also know that that is 30 degrees. And then at this point, we found like, well, almost all of the useful angles that are out there to find, right? Which means that we're probably at a point where we can easily go and answer this question here, where we've got to go find the size of DBC, right? Because as we said, simply having a lovely annotated diagram isn't enough. We need to be able to indicate how we got where we got, right? Okay, and now because there's so much going on in the diagram, it's actually not that easy to retrace our steps, right? So it might be a bit of an interesting thing. And this is one of the parts of using Dr. Cape Town that needs to be practiced, right? Once you've got this fantastic diagram with all the information in it, it's not necessarily trivial to get to the point where you can write down the answer, right? Because you've got to be able to retrace your steps, right? So we're looking for DBC. So I'm going to say, okay, DBC, that's there. That's where I'm trying to get to. And then I'm going to think what was given. I was given the 30 degrees, right? So the 30 degrees is going to be useful to me. And the 25 degrees I was given. Now, if I look there in triangle ACB, it looks like it's going to be useful to know that this was a 90-degree angle, right? And then it's also going to be useful to know that that was 25 degrees, right? So let's see how we put that together. So first, I'm going to start by saying that ACB is equal to 90 degrees. And there your reason is going to be the angles in the semicircle. Brilliant, right. Now that I know that this is 90 degrees, it's going to be very useful to know that this is 25 degrees, right? Because then I've got half of that angle B already, right? So how we do that is we're then going to say that this ABD, so this ABD is going to be equal to the ACD, the 25-degree angle. And our reason for that is angles in the same segment. Okay, so we've got the angles in the same segment, right? And now we're actually home free, right? Because we could tell that this whole thing is 60 degrees from the fact that ACB is a triangle, right? So in ACB, triangle ACB, right, we've got that the 180 is equal to the BAC plus the ACB plus the ABC, right? And then I'm going to continue there. Our 180 is equal to, so the BAC we said is 30, the ACB we got is 90, we've proven that, and that's plus ABC, right? And so ABC is then going to be 180 minus 30 minus 90, and therefore the ABC is equal to the 60 degrees. And then we're pretty much home free, because we can say that ABC, the 60 degrees, is equal to ABD, so that's now this 25-degree angle, so ADB, plus the DBC, right? And there we then have 60 was equal to ADB, so that was supposed to be ABD, sorry, ABD, which we said is 25. And then this DBC must then be the balance of that. So 60 equals 25 plus DBC. So 60 minus 25 is going to be the 35. Now I've run out of space there, but basically at the end, we can then say DBC is equal to 35 degrees. And that's what happens when we solve this equation here. Yeah, so that's how we got DBC. For those of you who got the 35 degrees, well done. You got the correct answer. For those of you who didn't quite get it, we do have these exercises on the website. and it was also distributed to you via email. So do go give it another try and see whether you can get the correct answer there. Okay, and then we've got to go prove that triangle EBC is equilateral, right? I'm just having a look at the time here. Okay, right. So equilateral triangles, we know are those where all three of the angles are 60 degrees, or all three of the sides are equal in length, right? So in order to do that, we've got to go show. So now we know this is 60 degrees, that we've already shown, right? It would be very useful to show that that is 60 degrees. So we know it is, but we've got to give a reason, right? So I'm going to say that CEB equals 2 times CAB, right? So CAB, this angle here, right? Which is then 2 times the 30 degrees, which is then 60 degrees. And this is where we get that angle at center equals 2 times angle at circumference. Okay, so now we know that this is 60 degrees because we showed that in the previous question, and we showed this is 60 degrees. But then as a result, BCE must be equal to 60 degrees because it's the third angle in triangle. Okay, and therefore we can say that EBC is isos, right? Because the interior angles are all equal. Okay, so that's then how we, oh, I said isos here, I meant equilateral. Okay, fix that. Nice. Okay, so that then was exercise 2, and now we can look at the final 2 letters of Dr. Cape Town. We've got P for parallel lines and T for tangents. So let's see how that is going to be applied. All right, so parallel lines, this has been with you for a long time already, right? You know that when you've got this F shape here, that's when you can get corresponding angles. And when you use this corresponding angles equal, it's a great idea to just indicate which lines are parallel. So here AB is parallel to CD. So in our reason, we want to just indicate that, right? Then if you've got this Z here, that's when you've got alternate angles, right? So alternate angles are also equal. And again, it's good form to just say which angles are going to be parallel. And then finally, right, we've got these co-interior angles, X plus Y, that must be supplementary, i.e. they add up to 180 degrees. So the co-interior angles are supplementary, that's our reason. And again, AB parallel to CD. Now, what's wonderful is the converse is also true, right? So here we've been given parallel lines and we find equal or supplementary angles as a result. If we are given equal angles or supplementary angles, we can also go conclude that we have parallel lines. And then again, I've harped on about this, but I won't stop, is that you can use what you prove. So as soon as you can show that you have parallel lines, that opens up more doors for you to go find some other angles, right? So here, if you've got these corresponding angles that are equal, XX, then you can go say that AB is parallel to CD, and your reason is going to be that corresponding angles are equal, right? Here, if your alternate angles are equal, you can again go say that you have parallel lines, and there you just have to say it's because alternate angles are equal, right? Or if you have co-interior angles that are supplementary, i.e. they add up to 180 degrees as 60 and 120 does, then those are going to be our co-interior angles. Okay, so parallel lines, probably not something new to you guys, but it is an important tool. And then for those of you who are in matric, right, we did promise here today that we're going to look at the grade 11 Euclidean geometry. But for those of you that are in matric, do also note that when you have parallel lines, you can also use your proportionality theorem, which is something to look out for. But then we're finally down to the last letter in our Dr. Cape Town, and that's going to be the tangents, right? So the tangent to the circle is perpendicular to the radius or the diameter of the circle at the point of contact, right? So where the tangent meets the radius or the diameter, that is a 90-degree angle, right? So it doesn't matter whether it's a radius or whether it's a diameter as it is there at the point of contact, those are perpendicular to each other, right? And your reason is going to be tan perpendicular to radius if it's a radius, or tan perpendicular to the diameter or a chord from the center or line from the center, right? So then the converse is also true. If you've got a tangent and a line that meets it there at its point of tangency, right, then that line is a line from the center. So it's going to go through the radius, or if you extend it all the way, it's going to be a diameter. So again, it's three pieces of the puzzle, right? Where if some other piece is missing, you can infer something else, right? So if you've got a radius that meets a tangent, right, then it does so perpendicularly. Or if you've got a line that meets the tangent perpendicularly, then that line is a radius or a diameter or something like that. Okay, so AB is going to be a tangent here, as we discussed, right? And then CD here, for example, will also be a tangent. And that's because of these perpendicular angles that were given there. And that's a line perpendicular to radius. Okay, so that line that we're referring to is the tangent, the CD or the AB, right? That's how you can claim it's a tangent. Okay, and then the theorem that I think in terms of its theorem statement confuses most people, and that's going to be the tan chord theorem, right? So the tan chord theorem says the following: the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the ultimate segment. Man, that is super heavy on terminology, right? So as we said, first step is to understand the terminology, right? And if you understand the terminology, maybe you've got a chance of unpacking this. So let's see if it can be unpacked, right? So we'll start by looking at the angle between the tangent to a circle and the chord, right? So here's our tangent to the circle, and here, for example, is a chord. So we're talking about that angle there that we've now got highlighted there in pink, all right? It's equal to the angle in the alternate segment, right? So we've got to know what the alternate segment is. So this here is going to be the same segment, right? Because that's where the angle is, right? So the alternate segment is that opposite one, right? So the alternate segment is this one there, right? And it's equal to that angle in the alternate segment. In other words, it's equal to that angle there. Okay, so that's the theorem statement for the tan chord theorem, actually explained in a way that hopefully you can understand if you understand the terminology, right? So basically this angle here between the chord and the tangent is going to be equal to the angle that that chord subtends in that opposite segment, right? So this angle is going to be equal to that angle, but then also note whenever you can apply the tan chord theorem, right, there's going to be two such angles if the tangent extends past this point. So sometimes the tangent just kind of ends here, and then obviously you don't have this green angle. But if you do have this tangent that goes along like this, then this green is equal to that green, this gold is equal to that gold there. And the reason here is simply the tan chord theorem. Okay, and then again, the converse is true, right? So our ingredients is a tangent to that chord where you've got the three points on the circle, right? And the angles that are equal, right? So here, if you're given that these angles are equal, right? And you've got these 3 points on the circle like you have, then you can go and infer or conclude that this AB is a tangent, right? So from what's given, if you can show that that X is equal to that X, then you can conclude actually AB is a tangent, and the reason is going to be the converse of the tan chord theorem. So the converse isn't something separate or something extra to learn, right? If you've got the tangent and you've got that triangle, you've got the equal angles. If you've got the equal angles, then you have the tangent. Okay, right. So a common mistake that we need to look for here, right, is that often somebody will that this X here is going to be equal to this Y here. And the reason they'll use is that tan chord theorem, right? Now, yes, it does look like this chord here is subtending that angle there, X. But again, that X needs to be an angle at the circumference, right? So all three of these points need to be on the circumference of the circle in order for the tan chord theorem to apply. So if your triangle only has 2 points on the circumference of the circle, no tan chord theorem for you. Okay. And then finally, we've got this here, 2 tangents drawn to a circle from the same point outside the circle are equal in length, right? So this is the common point here, B, right? So this means that AB and CB will be equal in length because they are tangents from a common point, right? And the reason is going to be tans from a common point. Okay, then something that's really interesting here is that when you do have tangents from a common point, that each meet a radius, right? So here we've got a radius there, and you've got a radius there. What's interesting is that it forms a kite, right? So why does it form a kite? Well, AB and CB are going to be equal in length, right? But then also the radii themselves are equal in length. And we know that when you've got a quadrilateral with the adjacent sides equal, so AB equals BC, and the two radii equal, then you do have a kite, right? And what's even more interesting is because of the radius meeting the tangent perpendicularly, right, that kite has right angles. And that means that if you separate the kite into two sides, you form two right-angled triangles like that. And when you've got right-angled triangles, there's often the opportunity to use Pythagoras, right? So for example, what often happens in analytical geometry is you know the coordinates of this point here, the coordinates of this point here, you don't know A, right? But you do know the length of the radius, right? I mean, you can use the distance formula to find the length of this. The radius is this. And then because of this that we've just discussed, you can conclude that that is going to be something you can find using Pythagoras. Okay, so then we can go on to our final exercise, right? Exercise number 3, right? And here we've got this lovely, beautiful rider where A is the center of the large circle. So we've got a big circle there, and A is the center of that circle. And then C here is the center of the small circle, right? AB is the diameter of the small circle, right? And DF is a tangent at F, right? So here's a point of tangency to the large circle. And then DB is a tangent to both circles at B, right? So it's a tangent to the small circle as well as to the large circle. And then we are told that BFD is equal to X. Right, so you've got to prove that FG equals GB. We've got to find 3 other angles that are equal to X, and we must find ABG in terms of X. Right, so we've got another poll for you. We're going to give you 4 minutes, and then you can give this a go. Okay, right, guys. I hope that you managed to give that a go. So let's see the result of the poll, please. Okay, right. So we've got x, 90 minus x, 180 minus 2x, and 90 plus x. I kind of feel bad for 90 plus x since nobody chose that. But let's see whether it is indeed the 90 minus x. So if we continue here, I'm going to, and again, I feel like you may not be surprised by this, but I am going to take this opportunity to go and apply to this Dr. Cape Town. Okay, so Dr. Cape Town, I'm going to start with the diameter, right? So the diameter that we've got is AB, right? It's the diameter of the small circle, which means this angle that it subtends is going to be a 90-degree angle. So I'm going to put that in. All right, that's the only diameter that we have, right? So now I'm going to look for radii. And I know that AB is a radius, but then something else interesting, right? Because A is the center of this large circle, AG is a line from the center, right? And it's a line from the center that's perpendicular to this chord here, FB. And we know that when you have a line from the center perpendicular to the chord, it is going to bisect that chord, right? And that's going to be our reason there why FG is equal to GB. So we've already got the answer to that question, but we're going to continue here. Right, so then R radius, okay, it's not that useful to make AC and C be equal, so I'm going to continue. The center we just used in a lovely way for this. For the center, it doesn't look like we have an angle at the center that's also being subtended by some chord that's subtending an angle at the circumference, so we can skip over that. Right, cyclic quadrilaterals, B, F, E are the only points on the large circle, so no. On the small circle, we've got B, G, A. I guess there's kind of this point there, but nothing's connecting it to like A, so it's not a cyclic quadrilateral, so no cyclic quadrilaterals. And then the other one is chords that are equal, and we don't have that information either that's been given. Parallel lines, not yet, and so we can jump through to the T for tangents, right? So we know that FD and BD are both tangents and they're tangents from a common point. And so we can go say that those tangents are equal, right? So we mark them as equal, but if then again, back into our toolbox, right? We know that we want to have our VIP tips with us at all points. And the I again is for isosceles triangles. So as soon as I mark this BD and FD as being equal in length, I'm going to go and mark this B well, this angle here as being X because they are the angles opposite the equal sides, right? Then what I'm going to do is I'm going to apply the tan chord theorem. So here, DB is going to meet here at X, well, at B, and it forms here this angle X with this chord, right? So then this chord BG is subtending this angle here, A, right? Which then means that that angle is also going to be X, right? So note A, G, B, they are all points on the small circle. And so we're not falling for that pitfall where only 2 points are actually on the circle, right? So we could say there that A is X, right? And then again, I always want to look for the third angle in a triangle if I can, right? So here, ABG is in fact the third angle of the triangle, that one there. I've got the X, I've got the 90. And so just to keep it nice and neat, I'm going to put that there and say that is in fact the 90 minus X. And so those of you who selected that for the answer, which was the majority, well done. It is in fact 90 minus X, right? And then if we continue from there, we can also apply the tan chord theorem in the large circle. So here, this F here, this line here, FD, right? It is forming this angle here, X, with this chord. So we've got that there. So then this chord is subtending E, and so this X must be equal to that E there, and we can put that as X. You can also use DB as the tangent that is going to give you E as the equal angle when you use the tan chord theorem. Right. And then again, in my toolbox, since I've got this as X and this as X, it might be super useful to just go label this one here as 180 minus 2X, because it is, after all, the third angle in a triangle. Okay, So if I look here at my time, I've got 6:31. So what I'm going to do is I'm going to end the actual presentation there and not write out the answers to these questions, because what's most important is that we understand why these things are the way that they are. Writing the reasons is the next step after actually being able to apply the theorems, right? So that's part of our being able to drive this car. Right, so then the final thing that we have on our agenda today is going to be the questions and the answers. Okay, so for this Q&A session, right, what you can do is you can please put up your hand using the Zoom functionality in order to do that, right? And then when you put up your hand, what I can do is allow you to speak. And when you then speak, I will be able to answer your question. Right, so please do also remember that the webinar is not over, so I'm done presenting, but there will be some information that we're going to give you at the end, just about how you can contact us, and also the competition that we'll be running in order for you to get the opportunity to have a free 1-hour lesson with Learning Space Tuition, where we can help you not only with Euclidean geometry, but all of maths and also all of physical science. Okay, so I'm now open for questions. If you do have a question, please raise your hand. Okay, so there's a raised hand. So now I just need to figure out how to find the person with the raised, Princess. Right, Princess, I'm going to allow you to speak. Princess, what is your question?
I wanted to ask you to please re-explain that, Dr. CPT.
Sorry, I'm just having a technical difficulty here that we just need to sort out with the team so I can hear Princess. Princess, do you mind repeating your question, please? Princess, if you could just once more.
Oh, I wanted to ask you to please re-explain the Dr. CPT because I got lost somewhere along the way.
Okay, thank you. So the question was to just re-explain this concept of Dr. Cape Town, because we a little bit got lost along the way, right? So the two most important things, as I view it, is to start with your Dr. Cape Town as a way to have a starting point, to analyze all the elements that are present in your rider, so that you can then find as much information as you can, right? So the first thing is Dr. Cape Town, right? So what we do is we start and we look for a diameter, okay? And then we apply all the theorems that apply to diameters, right? Then the next thing that we do is we look for radii, right? So when we have radii, we want to mark them as being equal in length, but then we also want to apply those theorems that apply to radii. Then the C3 is for the 3 C's. So the one is for the center, right? So when you've got the center of the circle, you've got the theorem about the angle at the center is twice the angle at the circumference, right? And you can also note that radii must always come from the center. So these things are connected, right? Then once you've applied that theorem, if it's applicable, then you can go look for cyclic quadrilaterals. So for the cyclic quadrilaterals, you're going to look for 4 concyclic points, right? So 4 points on the edge of the circle. And then you're going to look for angles in the same segment. You're going to look for opposite interior angles that are supplementary, and you're going to look to see whether you've got an exterior angle, which may will be equal to the opposite interior angle. And then the third thing you look for in terms of the C's is for chords that are equal, because chords that are equal are going to subtend equal angles. Then you're going to look for parallel lines so that you can apply the alternate corresponding and co-interior angles, as well as, if you are in metric, the proportionality theorem. And then T is to go look for tangents so that you can then apply the theorems that pertain to tangents, right? So this is a method of analyzing the diagram that's in front of you and extracting as much information as possible so that you are then able to answer the questions. So when we've got these complicated things in front of us, what often happens is we don't know where to start. Now you know where to start. The other thing is looking for elements like tangents and chords and applying the tan-chord theorem. That's always something that we've done implicitly if you just start by looking at the rider. Now, by using Dr. Cape Town, you can take that thing that is implicit and you can make it explicit by following a process, right? So if I, for example, am going to answer riders, because I've been doing this for years and years, I might not use Dr. Cape Town, right? But that's because I'm implicitly doing those things. I'm looking for diameters, radii, whatever, and then my associative memory is allowing me to use that, right? Now, if you haven't done that much Euclidean geometry, what this is allowing you to do is to then do that thing that you do automatically in a more structural and procedural way, so that you're less likely to get stuck. Thank you, Princess, for your question. All right. Charlotte, can we please have your question?
I wanted to talk about like there's this question where it uses the theorem angle at center is equals to 2 times angle at circumference, and then we get a question that says prove the theorem which states that let's say if the diagram is SOT is equals to 2 times SPT. Like, will you please explain how to properly get that answer?
Sorry, I started answering your question there, but then I was muted. Okay, so the proof for that theorem, I think what we can do, Charlotte, is if you, we'll note down your details here, and then we can send you the proof for that theorem, just because going through a proof for a theorem is something that might take 5 to 10 minutes. And that might not be of interest to all the panelists currently. So thank you for your question on proving that theorem. We will send through a proof of it for you. I just don't quite want to take the time to go through proving an entire theorem now. But thanks for your question, Charlotte. We will revert to you based on that. Okay. Please, if there's anybody else other than Charlotte and Princess, please feel free to raise your hands if you do have questions at this point. Okay, so we've got a question in the Q&A, which is asking us to explain the concept of parallel lines, right? Now, parallel lines is something that has come with us for quite a while in our Euclidean geometry, in that we've been introduced to parallel lines quite a few times in math. So the basic concept of parallel lines is that these are two lines that when you extend them forever and ever, right? So you make them longer and 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 longer. These lines will never meet, okay? So parallel lines will never meet, even if you extend them for the rest of your life. You keep drawing these lines longer and longer and longer, right? Whereas lines that are not parallel, like these, for example, if you extend them infinitely, at some point they will meet and they will then intersect, right? So parallel lines never intersect, right? And parallel lines we tend to mark with a little arrow like this here, right? So parallel lines is where we can then have what we labeled as corresponding angles, right? Or alternate angles being equal, like those there, or then also co-interior angles, where this angle here plus this angle here would add up to 180 degrees, right? In contexts other than Euclidean geometry, on the Cartesian plane, parallel lines are those that have the same gradient. So if this line has a gradient of 2 and this line has a gradient of 2, then those will be parallel lines and they will never intersect. Okay, right. Thank you so much for that question. We've got a question from Uhone. I hope I'm pronouncing that correctly. Uhone, please feel. Uhone, please feel free.
I wanted to ask if the Dr. Cape Town is applicable to every rider, or is it only applicable to some of the riders?
Thank you so much for your question. Okay, so to answer your question, sometimes when a rider is very simple, right, the Dr. Cape Town method isn't going to give you a lot of results that you're going to find to be useful, right? So for example, sometimes you get a simple thing where you just have a circle, you've got a diameter and maybe 2 or 3 other chords, right? So then the entire Dr. Cape Town method might not be as fantastic as you might want it to be in terms of giving you all the answers. Now, Dr. Cape Town still won't be wasted in doing that, because there has to be something. There has to be diameters or radii or chord or something like that. Otherwise, there's no theorems to apply, right? So all of the theorems that you need to know have something to do with diameters or radii or chords or something like that, right? So it's not wasted, but where it's really powerful is when you've got these incredibly complex riders with 15 marks or 10 marks or whatever worth of questions that follow on from it, where you look at the diagram and you're just like, my gosh, there is so much going on here. I don't know where to start. I don't know what to do. And you get that little bit of panic, you know? So that is when Dr. Cape Town really shines, because it gives you a place to start. It gives you something to work through, a methodology to work through, where you can say, I've started here and I've ended here. And hopefully when you're done in your diagram, you've got something that's going to be useful to you. So I don't think it's wasted to ever do Dr. Cape Town, but there are some riders where it's going to be more powerful and more useful than others. And that's going to be those very complex ones with many elements involved. Thank you for your question. Anybody else, please feel free to raise your hand if you do have questions. Okay, so I see there's a question here in the chat that says, analyzing a problem that involves 2 circles and extracting info may be tricky to learners. What is your advice on that? Okay, so my advice would be to see if you can view either circle in isolation at some point, right? So usually I would advise against going into tunnel vision, as I call it, where you're focusing on just one thing, right? But when you've got 2 circles, right, you can have so much that's going on that I advise you to first get tunnel vision on one and then tunnel vision on the other, right? So you can even, if you want to, apply Dr. Cape Town twice, once for the one circle, then for the next circle, right? So you can start with the one circle, look for the diameter, look for the radii, the cyclic quad, etc., for that particular circle, and then repeat the process for the other circle. So this has been, yeah, one time where I would say focus on each thing individually. And then once you're done and you feel that you've extracted all the information you can for the individual circles, then you can look a little bit at the broader picture and see what's connecting them. And as I said, if you've got your tool belt or your toolbox with you, right, and you're marking vertically opposite angles and isosceles triangles and all these things, finding your third angles and triangles, then you should be able to extract pretty much all the information that is there to extract in that particular rider. Thank you so much for this question. Right. Any more questions? Please feel free to raise your hand or to post it in the chat if you would prefer to do it that way, or the Q&A function. Okay, so I think we will then call it a day there on the content part of the webinar, but not yet on the webinar, because as I said, we're going to hand over to Ernest just to get some information on how you can get the opportunity to win a lesson with Learning Space Tuition, 1 hour, one-on-one, private, and hopefully that's the sort of thing that can really boost you to getting the sort of results that you want. From my side, I'd like to thank all of you so much for joining me and going through this journey with me. For those of you who asked questions, I greatly appreciate the questions and the engagement. I enjoyed this so much, and I'd like to let you know that this is not our last webinar. Not even close. So this is something that we're going to be doing frequently going forward, right? And as we go, we're also putting up interesting things on our website, resources, materials. We'll be making videos. Please stick with us as we go through this journey of building learning space tuition from already a fantastic offering to something that can reach all of you across the country. We saw we had people from every province. I'm looking so forward to engaging with you and possibly meeting some of you going forward. Thank you. Over to Ernest.
Thank you so very much. I call him, you guys can call him Mr. Cox or Heinrich Cox or Cox, as some people were just saying in the chat. I call him Henny. Henny, like I mentioned, guys, he's our academic manager. He looks over curriculum. He makes sure that academically we give you guys the most phenomenal. I mean, if you guys look at that presentation he just gave us, it was absolutely phenomenal. It blew me away, even though I'd seen it before, but it still blows me away every single time. Henny keeps working to make these presentations better and better and better every time. And that's just for you. As Henny has mentioned, we are going to be doing these webinars very regularly. Please be on the lookout on our website. We're going to keep posting on our website. We're going to post on our social media pages in terms of when they're going to be coming up. We'll be releasing a roster very soon of the next coming webinars. So as Henny mentioned, that really awesome competition that we're going to be running. We are basically going to be, like I mentioned in the video, if you guys saw earlier on, we're going to be picking a follower from Instagram. We're going to be picking a subscriber from YouTube. We're going to be picking a follower from Facebook. So please make sure, we're going to show the social media pages as soon as we're done with the webinar. Go follow on Instagram, go subscribe on YouTube, go and follow on Facebook, go to our website regularly. We're going to pick one person from each and every one of those social media platforms, and they will get the chance of a lifetime. This is a one-on-one private lesson with Mr. Cox himself. And I mean, for me, this is one of the best maths educators we have in the country, hands down. I used to think I was the best until I met him. He just sort of proved me wrong. So please go like, go subscribe, go join, just follow us every single place you can. And now there's one that's even better than that. So remember, as Learning Space Tuition, we don't only do these kinds of webinars. Mondays through to Saturdays, we are having afternoon sessions, tuition sessions, where you can actually come and sit with one of our many members that are part of our team. This isn't just the two of us. There's many tutors that are part of our team, the Mutsas, the Tsapangs. Go to our website, get to meet the team that we have at the Learning Space Tuition. And what you guys can do, if you go and follow our social media platforms, you can stand a chance to win a free lesson with one of the other guys. But before the competition comes, just give us a call, right? Go on our website, find out what's email us at info@thelearningspace.co.za and actually ask to speak and engage with one of our tutors. Get to have a lesson. I know a lot of you had questions that need more time, spend time with our tutors, because one of the phenomenal things about our tutors, they are so well trained. They have so many years of experience, and they are phenomenal mentors. They will sit with you, they care, they spend time to get to understand your academic needs, and they'll get to teach things in a way that you will be able to understand, similar to Mr. Cox, who trains all of our educators. So this is just a taste of what you guys can find at the Learning Space Tuition. So please, guys, make sure that you go and subscribe to all our social media platforms, get in touch with us, get in touch with one of our tutors, and get connected to them. As this brings us to the end, we want to thank everyone who came and joined. Thank you for giving up your time. Join us next time. Thank you to Mr. Cox for the phenomenal presentation, as well as the Learning Space team for the support. I want to give a big shout out to the Brobean Studios team who are giving us the beautiful, I mean, look at these visuals, guys. I mean, I'll flick again, look at me in super HD. These are phenomenal visuals by the Brobeans team, and I want to thank them very much for being behind the camera. You don't quite see them, but without them, this doesn't happen to this level. This isn't a pixelated webcam feed that you're seeing. So I want to thank them a lot. Yes, this has been a phenomenal time, and we're going to go do our final poll now, just to sort of see how you guys did. I'm going to ask our technical team to run the poll, but thank you very much from me.